Hi everyone, I'm Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. So today we are going to discuss about filters concept, and specifically we are going to discuss inductor filter. So overview of the today's session: filters, inductive filter, and conclude with summary. So what is the importance of filter? So if you consider a rectifier, so what will be the rectifier output? So we know the rectifier output is not a pure DC. So that means it is a pulsating DC. Rectified output is pulsating DC. So that means it consists both AC plus DC. Okay, but to function an electronic device, we require only DC component. So therefore, this AC component we don't require. So that is called ripple. So we have to remove these ripples. So to remove these ripples from rectified output of any rectifier circuit, we require additional circuit. That circuit is called filter. Okay. So filter, what it do? To minimize ripples in the rectified output, we use filter circuit. Okay. So if you observe this waveform, so this is a full wave rectified output, which is not pure. It is not pure DC. So it is a pulsating DC. So that means it consists both AC and DC. So we don't want this AC component. So in order to remove or minimize this AC component from the rectified output, we require this DC component. Okay, we require this filter circuit. So ripples are varying with time, that is AC component. So they vary with time, whereas DC is constant with respect to time. It does not change with time. So it is constant voltage. So this type of DC, pure DC we require. So therefore, filter circuit has components that have low impedance and high impedances, like inductor and capacitors. Okay. So if you observe the block diagram of any filter, so here filter is there, filter, and here we are applying input voltage, that is rectified output from full wave rectifier or bridge rectifier, and this is the output. So the output will be observed across the filter. So this filter, it may be capacitor filter or inductor filter. So the output contains AC component will be removed or minimized. Okay. So this is the basic concept of filter. So specifically today we are going to discuss what is inductor filter and how we can analyze. Let us see. So inductor filter. Inductor blocks AC and allows DC to reach the load resistor. Okay. So the basic property of an inductor, it blocks AC component and allows DC component to reach the load resistor. So if you see the ripple factor of this circuit, so rho is equals to RL upon T 3 root 2 omega L. Okay, so ripple factor is given by RL upon 3 root 2 omega L. So here RL is load resistor and L is the inductance and omega is the frequency. So this filter is more effective when the current is more. That means what? So by observing this expression, what happens? This filter is more effective. So it will works effectively when the load current IL is more. If load current is IL is more, means what? It should be RL should be very less. So if load resistor is small value, then your inductor filter works good. The larger value of the inductor reduces ripple, but at the same time output voltage is also lowered. So the another important point is, if you use inductor value, large inductor value, of course ripples removed or reduced, minimized, but at the same time the output voltage is lowered because the inductor offers high resistance. So therefore inductor opposes any change in the current. So this is another important point or property of an inductor is inductor opposes any change in the current. With this property we can utilize or we can analyze further the induction filter. So let us see how to analyze the inductor filter. So let us analyze this inductor filter for a full wave rectified output. So I consider the full wave rectified output, and the expression can be written using Fourier series. Output voltage is given by 2 Vm by pi minus 4 Vm by pi and so on. So this is the, if you observe this expression, 2 Vm by pi is DC component, DC value, and remaining are AC component. So assuming third and higher terms contribute little output, the output voltage is here V0 is equal to 2 Vm by pi, 4 Vm by 3 pi cos 2 omega t. So we consider only third term and higher order terms. So that contributes some little amount of voltage. So here we have to neglect diode resistance, choke resistance and transformer resistance, because so in your rectified circuit, so we have secondary coil resistance, okay, and here we are using diode. So diode has its own resistance, and also here we are using inductor. Inductor also has, so sometimes called choke. Inductor is nothing but choke. So this has its own resistance. So by neglecting these resistances, why? Because RL, the load resistance, has more value compared to these three resistance values. So therefore we can neglect diode, choke and transformer resistance. The DC component of current IM is given by Vm by RL. So the impedance, now let us consider the impedance of series combination of L and RL at 2 omega, second harmonic frequency. So 2 omega. So then that means, so we have L and in series with the RL. So series combination of L and RL, load resistor and inductor, the impedance is given by Z is equals to root of RL square plus 2 omega L square. So which is given by 2L square plus 4 omega square L square. So let us further analyze this. See here, for the AC component, IM can be written as Vm by RL. Actually, so DC component we can write directly Vm by RL. So but we consider impedance. So inductor, load resistor we have to consider. Series combination of load, inductor and load resistor. So in such case we consider this, for the AC component IM value can be written as Vm by root of RL square plus 4 omega square L square. In place of RL we have written this. So resulting current is given by 2 Vm by pi RL minus, so if you substitute this value in this, so 2 Vm by pi RL minus 4 Vm by 3 pi cos 2 omega t minus pi upon root of RL square plus 4 omega square L square. So where this, what is this pi? Pi is tan inverse 2 omega L by RL. So omega is frequency and R is the inductor value and this is load resistor. So now what is the ripple factor? So let us see the ripple factor. Ratio of the RMS value of the ripple to the DC value is the ripple factor. So ratio of RMS value to the DC value of the wave. So which gives the ripple factor, and that is expressed as this point. So this is the expression for ripple factor of the inductor filter. So it is 4V, that is, this is your RMS value. So RMS value of the ripple by, this is the DC value. So 2 Vm by pi RL and this is the RMS value. So if you substitute all these values, so finally you will have this one, this expression you get. So here in this, so if you consider, if 4 omega square L square by RL square, this term is greater than, much greater than 1, so then simplified expression for ripple factor is given by RL by 3 root 2 omega L. Why? So because we have considered that 4 omega square L square all square is compare to more than 1. So we can simplify further the ripple factor expression as load resistor RL upon 3 root 2 omega L. Okay. So if the load resistor is infinity, for example, in this expression, so in the circuit diagram, so if the load resistor RL is infinite, that is 0 current. So RL is equal to infinite means 0 current. So in such case, the ripple factor can be written as R is rho is equals to 2 by 3 root 2, because we can neglect this one. So we will find only this 2 by 3 root 2. So we can neglect this because RL is infinite. So RL is infinite means, so you will get 0. So 1 by root 1 is 1 only. So finally you will get this 2 by 3 root 2 only. So finally you will get the ripple factor of the inductor filter as 0.471. And if you compare this with the ordinary full wave rectified output, so what is the ripple factor for full wave rectifier? It is approximately 0.48 something. So that means, of course, it is nearer to the ripple factor of the full wave rectifier, but somewhat decreased. The ripples are decreased using inductor filter, okay, compared to the full wave rectifier. So the pulsating DC can be in pulsating DC, the rectified output of full wave rectifier, the ripples are removed somewhat compared to the rectified output of the full wave rectifier. Okay. So, but very minute change. Whereas, so therefore, we can conclude that so the difference being attributable to the omission of higher harmonics as mentioned, it is clear that the inductor filter should only be used where RL is consistently small. So inductor can be used only when high current through the load resistor or RL is very small. So if RL is very small, then the inductor filter is very effective. So this is the concluded statement. So therefore, so this concludes your today's session. So today we have discussed what is filter concept, what is filter, so what is the importance of filter. So because in the rectified output we have both AC and DC component. So therefore, to remove AC component we use filter circuit, and then we have discussed filter inductor filter, and we have analyzed the inductor filter. So I think next topic will be capacitor filter. Thank you.